Okay, welcome to the session on limiting reactants. The objective of watching this video is to get you to feel much more confident in identifying limiting reactants. The limiting reactant problem is probably a lot of students find it to be the most anxiety-provoking of stoichiometry problems. So I'm hoping that in 5 or 10 minutes you'll be feeling a lot better about that. Okay, so first example. In this example, it's not really a chemical reaction, but I'm describing a process of making a bicycle. 2 wheels plus 1 frame results in 1 bicycle, and you should be familiar with the format I've got here. So I'm using the BCA table. Remember, B is for before the reaction, C is the change that occurs during reaction, and A is after. What's the result after the reaction has been completed? So before, change, after. And then here's some space for calculations if we need them. Now, if we have a situation where we're given 10 wheels and 5 frames, I think you can see that we've got, we have the perfect ratio of those 2 bicycle parts for making 5 bicycles. And so hopefully this seems pretty intuitive. Now, in the world of chemical reactions, however, it's not usually the case. You don't usually get to work with perfect ratios of compounds. A lot of times you're not going to have them in stoichiometric ratios. And so in those cases we have to be able to figure out how much product we get to make based on the imperfect amounts of reactants that we're given. Alright, so here's a different scenario. And again, you can probably see if we have a situation where we have 10 wheels and 10 frames, I hope you can see that we're still only going to be able to make 5 bikes because we're limited by the 10 wheels, right? Each bicycle requires 2 wheels, and so we're going to make 5 bikes. And because we have 10 frames, that's great, but we're going to have 5 frames left over at the end of the assembly process. Okay, so that probably feels pretty clear to you intuitively, but what I'd like to do, if you just bear with me, is I want to illustrate the approach, the strategy that I'd like you to try to use when you face a limiting reactant problem where the numbers are not very nice looking and the ratios are not as simple as this. All right, so here's the approach. Step 1. Look at the amount that you're given of the first compound. All right, we have 10 wheels in this case, and you ask yourself, okay, if I'm given 10 wheels, then how many frames would I need to completely use up those 10 wheels? Okay, and to do that, you need to look at the ratio between those 2 reactants. It's 2 to 1, so you only need half as many of these as you have of these. So if you want to completely use up the 10 wheels, you're going to need 1/2 of 10, which is 5. And then you compare that with what you were actually given, which is 10, and then you realize, oh, not only do I have 5 frames, I have a surplus. I have more than I need to completely use up the 10 wheels. And so therefore, the frames becomes because it's a surplus, you have more than you need, you have an excess. That's just another way of saying that. And this is the term that we use in chemistry to describe the compound that we have more than we need. Okay, and if that's the excess, then the wheels are the limiting in this case. Pardon my writing. Okay, and if the wheels are limiting, then this is the compound that we're going to use to determine all of the other amounts. Okay, and by definition, if the wheels are limiting, we will use all of them up during the course of the reaction, so there will be 0 wheels at the end. We will have run through all of those. We determined that we were only going to need 5 of the frames, so we're going to run through 5 of the frames, and that means we're going to end up with 10 minus 5 is 5, so we'll have 5 left over. And in the process, because the ratio between frames and bicycles is 1-to-1, if we use up 5, we're going to, you'll be making 5 bicycles. And of course that's 0 at the beginning, right? Okay, so very simple example. A very familiar scenario, bicycles. We're all familiar with that, and that's that's the recipe right there. That's I think a very good approach to use on the other limiting reactant problems that we're going to face. Okay, here's another case, another situation. Let's try this. In fact, why don't you pause the video and use the procedure that I showed you on the last one and see if you can do this one. Okay, so hopefully you started with the 10 units of A, and then you asked yourself, okay, if I have 10 units of A, how many units of B will I need? And to do that, you have to key in on the stoichiometric ratio between A and B. That's 2-to-3. And so to figure out, how many B's am I going to need, we have to, you might be able to do this in your head, okay? You can see that, if it's a 3-to-2 ratio, that's, we're going to need 1.5 times more A's, more B's than we have A's. And so you're going to need 15. Okay, so maybe you can see that intuitively, but let's do the calculation just to be, make sure we know what we're doing. So the question is, how many B's are we going to need? All right, so the number of B's that you'll need is equal to the number of A's that you have. Okay, so we have 10 A's, and then you simply multiply that by the ratio given in the balanced chemical equation. And since we're interested in finding out about B's, we put the coefficient for B on top and then the coefficient for A on the bottom. You can see the A's cancel out. And when you take 10, multiply by 3, that's 30. 30 divided by 2 is 15. And so we're going to need 15 B's. And, which is exactly what we what we thought we would need. All right, so then you take that number, the number of B's that we need to completely use up the A's, and we compare that number with what we were given. All right, and obviously we're a little short. We do not have enough B's to completely use up the A's. Therefore, the B's are going to be limiting. The number of B's that we were given is going to limit the number of C units that we're going to be able to make. Okay, and so then what that means on a practical level is, when you go ahead and carry this forward to calculate all of the amounts that are left after the reaction, you're going to use that number. Okay, so this is the number that you'll base it on. Okay, let's try another one. I'm going to go a little bit faster now because we're not focusing on calculating all of the the amount of products and the change and all that. We're just trying to isolate the skill of identifying the limiting reactant. All right, so give this one a try. Okay, hopefully you paused the video. You gave it an honest attempt. So we start by saying, okay, we got 15 A's. How many B's would we need to completely use up all the A's? All right, that's the question. So here we want to know how many B's do we need, and so we start by saying, well, we have 15 A's, and to figure out how many B's we need, we'll have to use the ratio between these two. So we have 3B on top, 4A on the bottom. And when you do the math, you should get 11.25. Okay, 11.25. The A's cancel, by the way. And I think you can see that, do we have 11.25? Yeah, we sure do. In fact, we have a little bit more. Therefore, since we have a surplus of B, that is excess. Therefore, A is limiting. And so for the purposes of finishing the rest of the calculation, you're going to base your calculation on the 15. Okay? All right? Let's try another one. In fact, for brevity, okay, I'm going to skip ahead. Let me do this one. All right, so here's a real chemical reaction. I think you've seen this in class. And let's say we're given 20 atoms of carbon, 9 molecules of sulfur dioxide. Which one is limiting? Okay, so again, start with the first reactant. We have 20 atoms of carbon. How many molecules of sulfur dioxide would we need? Well, let's just do a common sense check. Based on the mole ratio between the carbon and the sulfur dioxide, 5 to 2, do you expect us to need less than 20 molecules of SO2 or more molecules than 20? Hopefully you're thinking, we need less, right? Because 2 is less than 5, and so, we're going to need something quite a bit less than 20. All right, to determine what that requirement really is of sulfur dioxide molecules, we start by writing 20. So that's 20 atoms of carbon, and then we multiply it by the mole ratio, which is 2 moles of SO2 divided by 5 moles of carbon. Okay, so that's 2 over 5, which is basically, that fraction equals 0.4, and multiply that by 20, and you get 8. Okay, so what that means is if we want to completely use up these 20 atoms of carbon, we're going to need 8 molecules of sulfur dioxide. Well, do we have enough? Yes, we have that plus one more. So we have an excess of sulfur dioxide. And what that means is the amount of carbon that we were given is limiting us. Okay? So now what that means is the rest of this problem is going to be based on 20 atoms of carbon. And so why don't we go ahead, and for this one I'll carry it through all the way to the end. So if the carbon's limiting, by definition we're going to run out of it at the end of the reaction. Okay? Over here we determined that, I'm sorry, let me fill in the change. Okay, so we're going to go down by 20. Over here we said we're going to need 8, and because this is the excess, then that's how much we're going to use, and we'll have 1 molecule of sulfur dioxide left over. Okay, over here we start with 0 of each. If you notice, now that we're talking about products, let's look at the ratio between the carbon and the first product. That's 5 to 1. So what that means is we're only going to make 1/5 as many molecules of carbon disulfide as the number of carbons that we put in. So if we use 20 carbon atoms, we're only going to make 1/5 of 20 molecules of carbon disulfide. Okay, 1/5 of 20 is 4, so it looks like we're going to make 4 molecules of carbon disulfide. And then here, now, when we're thinking about how many molecules of carbon monoxide we're going to make, rather than going all the way back to the carbon and using a 4 to 5 ratio, I'm just going to do a little shortcut here, and I'm going to say, well, for every 1 molecule of carbon disulfide, my balanced chemical equation says we're going to make 4 molecules of carbon monoxide. So we'll make 4 times this many. We're going to take the number of carbon disulfide molecules, multiply that by 4, and that tells us how many molecules of carbon dioxide we make, right? Okay, so that's that. Let me just check my time. Okay, looks we're at the 15-minute mark, so I think that's enough. I hope this was helpful, and thanks for listening. And we'll see you soon.